Hi guys, we're going to have a look at example 12.9 here. This is chapter 12.5 on curvilinear motion, rectangular components. So just recall what I said earlier is that in the previous video I said that with regards to curvilinear motion, we can analyze exactly the same motion, right? This particle is moving in a curve, it's curved motion. We can analyze it using different coordinate systems. And the one we're doing now are these rectangular coordinates. We are going to do normal and tangential coordinates. And then there's another one which is cylindrical coordinates, which we will not touch on in this course. But the point is, just to give you a bird's eye view, we analyze a particle using different types of coordinate systems depending on what kind of information we have. Okay, and sometimes it's better to use rectangular coordinates to analyze that motion. Sometimes it's better to use normal and tangential coordinates. Okay, but the point is 12.5, we're looking at rectangular components. Okay. So, with regards to this problem, 12.9, okay, it's a pretty standard problem, but as I said in class, I don't like the way they jump into the solution, even though it's 100% correct, okay? The reason I don't like it is because in 12.5, the theory, they begin by saying, okay, if I've got a particle in space, and we're using rectangular coordinates, the first thing we do is we define the position vector. Let's define the position vector. Then, if we want velocity information, then from that position vector, we can get our velocity, and from velocity, we can get our acceleration. Okay, that's the general idea. But then when it comes to the problem, they solve it, but they don't lay it out in that kind of way. All right? So let's just look again at this problem. This is a curvilinear problem. We're analyzing it using rectangular components. A balloon moves from the house along this curve, y equals x squared over 10. Okay, so take note there. There's the curve, y equals x squared over 10. So y is a function of x, and x is a function of time. Y is a function of x, and x is a function of time. So there's our curve, looks like that. And this curve is given by y, x squared over 10, and x is given as 8t. Okay, so I've got y as a function of x, and I've got x as a function of time. Okay, so this is y, and that is x. So based on the theory, let us start by writing out what is our position vector. What is our position vector? Okay, that is the general form of our position vector using rectangular components. See, the textbook doesn't do this. They don't do that. They just try to jump into analyzing one of the components and they move on from there. So the question is, what is the question? It is, determine the magnitude and direction of the velocity and acceleration at time equals 2 seconds. Determine the magnitude and direction of the velocity and acceleration at time equals 2 seconds. Okay, very good. So if I want my velocity, how do I get it? I first need my position, because velocity is dr dt. Okay, so let's start with position. The textbook doesn't do this. Okay, it does do it, but it doesn't lay it out in this form. I like this form. It makes sense to me. So there's my position vector. What is x? X is given by 8t. So let's put that there. 8t I. And what is y? Is x squared over 2. X squared over 10 j meters. But then we can go further because we know that x is a function of time. we can substitute this into there. And if you do that, if you substitute this, the 8t into there, you're going to get 6.4 t squared j. All right. So this is really great because now I've got both my, remember, position vector is a vector. It's got an x component, it's got a y component. And if I want my velocity is dr dt, 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 dt. So if I had it in this form, then this would have been easy. I would have gone ddt of this, straightforward, because it's already as a function of time. But this, I would have needed to use the chain rule to solve this, okay? But because x is, I have the explicit function of x as a function of time, I can plug that in and get both my x and my y in terms of time. Okay, so what is v then? It's dr dt, which is then, what's d dt of that? 8 in the I, 8 times I, plus, what is d dt of this? 12.8 t j meters per second. Excellent. We're looking for our velocity, magnitude and direction of our velocity. So this is how I like to do it. Now I've got, the reason why I like this is then it's basically like I see the whole plan. I see the whole picture. I see where everything fits in. The textbook does not do it this way. They extract only one of these components and then they work with only one of them, but you don't know where everything fits in. I like using this method because I can see where everything fits in. I know where everything is positioned. So there we go. I've got my velocity function, my velocity vector function. Now, so tick, excellent, I've got it. Now I can go determine my magnitude and direction. The magnitude of my velocity is equal to, by the way, I just want you to see here, that whole thing is Vx, that whole thing there is Vy. Okay, V vector is Vxi plus Vyj. Okay, Vx and Vy, so that whole thing there in front of the I is Vx, the whole thing in front of the j is Vy. So what is my Vx? It's 8 squared plus what's my Vy? 12.8 t squared square root. This is my magnitude. But what is t? At t equals 2 seconds. We can plug that in and we calculate this and we get the magnitude, which is of velocity, which is really the speed, is 26.8 meters per second. Okay? And so at that point that we're looking at, that velocity vector must be tangent to that curve. Okay? So the speed is 28 meters per second. So at that point, as it's going there, at that instant, the velocity, the magnitude of the velocity, which is the speed, is 26.8 meters per second, and it's going tangent to that curve. Now, what is that angle? What is the direction? Theta is tan to the -1 of, okay, maybe I should just quickly draw the velocity vector diagram. Always do this. There's my Vx, it's my Vy. What is my Vx at t equals 2 seconds? At t equals 2 seconds, my Vx is 8. Let me just pause. Okay. And my vertical velocity is what? It's 12.8 times 2 seconds. And what is that? That would be 25.6. So there's my V, Here's my Vy, there's my Vx, and we just calculated the magnitude, okay? Calculated, that's the magnitude, which we calculated there. But then what is the angle there? It's equal to the opposite, it's 10 to the minus 1, opposite over adjacent, which is 25.6 over 8. And that gives us 72.6 degrees. Okay? So we know that this angle 72.6 must give us a tangent to that curve there. So that is our theta v, which is 72.6. Okay? So we've calculated our magnitude and we've calculated the direction of our velocity. We still need to, by the way, just as a test, if you get something like 110 degrees here, which means that you've got a velocity vector pointing there, then you know it's incorrect because it must be tangent to the curve. Okay? So that's why that helps as a test, as a validation. But now we also want acceleration. Okay, we want the magnitude and direction of the acceleration. So again, this is why I like to write it out in this vector form. AXI plus AYJ. And we know that A is just d dt of V. All right? So what is our AX? Our AX, what was V? V was given by 8I plus 12.8 T times J meters per second, right? Again, this is how I like to do these problems because it gives me the big picture. I see where everything fits in. Now, what is A? A is d dt of V. So what is the change in time? What is the change of this over time? It's 0. What is the change of this over time? d dt. It's 12.8 J meters per second squared. Okay? So there we go. There's my acceleration vector. Wonderful. And so we can see the only, so now what do we want? We want magnitude and direction of our acceleration. How do we do that? Again, ax squared, ay squared, square root. But what is ax? It's 0. Ay is 12.8 squared, square root, which is just 12.8. And you could just, I just did that just so that you could go through the whole exercise. But you can just see if it's only got one component, then that is the magnitude, right? Well, the positive of that value is the magnitude. And let's draw again our acceleration vectors. There's our ax axis, our ay axis. We don't have any acceleration in the x direction. We've only got an acceleration in the y direction. So there is our, and it's constant, right? It's constant. It's not a function of time. Is 12.8. So we've only got something happening in the y direction. So what is the acceleration direction? It's 90 degrees. Again, if we draw that curve at that point that we're looking at, t equals 2 seconds, our velocity should be tangent. But what is our direction of our acceleration? It's straight up. There's our acceleration vector. And does that make sense to you? Yes. It does make sense. Why? Because the acceleration vector must be on the inside of the curve. It must be on the inside. Inside of curve. Okay? Why must it be on the inside of the curve? Just because we feel like it? No. Because the reason why it's going in that curve is because it's accelerating towards the inside of the curve. All right. Okay? So I think that is the important thing that I want you to just take away with just is that y was a function of x and x was a function of time. So because we had x, an explicit function of time, we could substitute that into there and we could get our position vector functions of time, which made everything a lot easier, okay? But there are problems where we do not have x as a function of time. We only have y as a function of x. And so what that means is we need to then carry out the chain rule. Okay? So make sure that you revise the chain rule. Okay, cheers guys.